Hello and welcome. Thank you for taking the time to attend this webinar. We'll be covering information related to generative design and how you might want to get started using it in your organization. My name is Brian Verbort, and I'm a solutions engineer here at M2 Technologies. So our agenda for today, a specific topic, is that related to generative design. We're going to go through the process from beginning to end, and that includes preparing your design for the generative process, identifying key geometry in your design that may need to be respected and preserved, supporting the design itself so that we can apply loads and forces and subject it to a working environment. In addition, we've got the generation, we'll be covering the generation of the reference geometry, as well as the comparison of that reference geometry and the shapes of the geometry on your screen, or that you may already have on your screen. This is just a brief snapshot. It's not too detailed here, but the information we're going to be covering is related to a skid-based folding panel design. And we're just going to focus in on one of those triangular panels and work through the process of getting it run through the generative design process. I'm going to be going ahead and opening up the Inventor application. All right, so the panel that we're going to be working on, again, it's just a standard triangular component. We're going to be loading into memory here and taking a closer look at. Hopefully you will be able to see my screen. There we go. So I should be sharing my Inventor screen with you at the current moment. And you should see in that Inventor canvas one of the triangular panels that we saw kind of a brief overview of. The idea here is to be able to take the panel that we've produced and it's already been fabricated, and we're going to optimize it to reduce the amount of material that's required to make this component, and obviously that's going to help you obtain your sustainability goals as well as your design goals. So one of the first things that we're going to do for that, or in that effort, is to take a look at the effort that was made previously when this panel was originally designed, to maybe do some light weighting and the reduction of material required to make the component. You can see that in the form of those triangular shapes and the slots that are included on this particular panel. Let me just do a little bit of looking around here so that we can see a little bit better. So from an isometric view here, we can take a look at it. Just kind of get an idea of what this panel looks like. I'll also point out that here in this panel design, we have some features that are important to us that we need to preserve, that we wouldn't want to be modified in any way. Mounting locations and things of that nature that are part of the core design and how it interacts with the rest of the assembly. So one of the things that we're going to do here is, I don't necessarily have to clean up this previous effort and the triangular shapes that you see here in that light weighting and material reduction effort, but it will help us to stay a little more focused on our efforts that we're going to be making now. So know that this isn't a requirement, but a lot of times you do want to do a kind of a pre-process on your designs to remove unwanted or unneeded information to reduce the calculation times, etc. I'm going to be using the delete face function that's built into Inventor to just simply window select those shapes that we're going to be just removing, so that we don't have to worry about being confused about our current effort and a previous effort. In this case, I want to make sure that when I'm using that delete face function that's in Inventor, I'm going to be healing the remaining faces, which then leaves us essentially with a blank slate. We've got the boundary of the object and all the geometry associated with it, but we've got kind of a blank slate to start with as far as the optimization that we're going to be running. At this point, we want to make sure that, and now that that effort's been made, how do we enter into and start working in the generative design environment? And how is that found? Where is that located? And I'll just point out that there are a couple ways to do it. I'll show you one now, and then we'll take a closer look at one of the other methods later. So on the ribbon, this is Inventor 2022, and on the ribbon, there's a shape generator option that launches the shape generator environment. This comes up just with a brief description of the product and the workflows, which is exactly what we're going to be going through today. So we'll skip that and we'll cover in detail as we move through. So with the shape generator environment active inside Inventor, we now see we've got a different set of tools available to us on the ribbon across the top here. We've got study and several of the items here. Most of them we will certainly go through. Know that the workflow that Autodesk has put together for this product makes sense in the fact that you're going to be working from left to right. So we can see that by creating, entering into the generative environment, we already have a shape generation study that's been created for us, just a generic name of Generator 1. We could rename that to give it a more descriptive label if we wanted to. We've already got a study that's been opened up and activated the generative environment. That's what matters. We could take a look at the information that's already in this design. When it was designed initially, or if I'm designing from scratch, which is certainly possible here as well, then I can go in and I can either add material or modify an existing material. You'll see that the material for this model is a mild steel. You'll also notice that I can pick from any other material types that are already available to us. And if you're familiar with Inventor, you've got your material library that's available. The other thing that we can do is we can determine what methodology do we want to use to calculate the success or failure of our efforts here. And so the material, we're going to be using the yield strength of the material for our calculations. And we'll also take a look at some safety factor safety information a little bit later. So I'm not essentially making any changes here, although I could, and adjust the material that's being applied. I'll cancel the dialog box. So knowing the material that we have and our goal kind of in mind is to increasing sustainability by reducing material, we'll go ahead and start working through by anchoring or securing the model here that we're planning on using the generative design tool against. So as we start to apply loads, we need to constrain this model somehow in space. So I'm going to simply do that by just spinning around on the underside of this model. I'm going to highlight the mounting face that will be secured, fixed in place for the resulting loads to be applied against. So selecting that face, you can see leaves a little glyph, a little icon here, so we can identify it. And I can just simply select OK in order to apply that. You'll notice that as I've added that icon, again, the glyph is there, but we also have all of the features and elements of our design here in our generative efforts are being applied and visible to us in the browser, much like we're already comfortable with in Inventor. So if I look at the constraints node, we'll now see our fixed constraint, number 1, shown there. And you'll see the cross-highlighting occur in the canvas for us to easily identify, and then we can always come in and we can modify these items that are in the browser as well after the fact. So we've got it fixed across the bottom. We know how it's going to be supported. Now we're going to apply a little more information or a little more requirements against it. We've got many constraints or loads that we can apply. We've applied the constraint already, many loads we can apply. In this case, I can take a look at the list of loads that are available to us from the drop-down. I can pick forces or pressures from above. I'm just going to do a force, and that force location is going to be the upper face. So we've got this angle sloped face here. We're going to be applying a force to, and if I take a look at that from the front, you can see the vector of that force is good, perpendicular to that face. And then I'll be quantifying that load, that force. We'll go with the 400 pound. Okay, with force applied and a fix on the geometry itself, we can then move forward and we can do additional forces. In this case, we'll keep things very simple. That's the name of the title, part of our title for our event today. So I'm going to move forward, and we're just going to simply add gravity at this point. And gravity is a thing. It is a force. It acts on something around us. And they've preloaded or predefined gravity force, so we don't have to remember the value for gravity. It's going to be simply asking us for a location to apply that gravity, and then we use the same face that we use to fix or support this particular design. Then we may notice that gravity is going the wrong way. In this case, it just assumed and made an assumption might pick the planar face, it went perpendicular to that, which is okay, but the vector needs to be corrected. So they give us a convenient button here in these the force application dialogues to make adjustments to those things. So now, having assigned a material, fixed the geometry in place, and added forces, including gravity, we now start to turn our focus onto the items that we don't want the generative process to influence, change, or modify in any way. And so those are what we term as preserves, or preserved regions, or preserved features. These are areas we want to make sure don't get modified or interfered with, that the generative tool will stay clear of, essentially, and won't be part of, these items won't be part of its process. So we're really just excluding things that are fine the way they are and need to stay the way they are. So those are obviously things like mounting fasteners and locations and holes for the fasteners to run through. So this is exactly what I'm going to be doing here, is I'm going to be zooming up on some of these smaller areas where we've got bolting connections that are passing through. We're going to be making adjustments to those. I'll go ahead and start a preserve region command. It's made for this particular specific purpose. And then it wants to know the location. Okay, what is it you would like to preserve? So in this case, I've zoomed up and I'm selecting not the circular edge, although I could. The whole purpose here is that we want to preserve the entire cylindrical face. We don't want that location and that through hole to be changed, altered, removed, and modified in any way. So once I've set that up or selected it, you'll see, because what I picked was circular, it's created a cylindrical bounding object. And this thing's editable. We can make modifications to its size. You notice as I make these changes here, just by dragging the glyphs, the manipulators in Canvas, that the values for the radius of that diameter are updated. This is important because it's not just the hole I want to preserve. I need some bounding surface around the hole for the fastener to bear upon. And so obviously the hole is a lack of a feature, and we need it to have some, otherwise the bolt will just drop right through if we didn't have a bearing surface. So all I'm going to do here is just define the radius rather than dragging it. I know something about our fastener and the bearing head underneath that fastener. So I'll go ahead and make an adjustment here, and I'll go with a 0.3. You'll see that it updates the diameter and the radius of that previewed geometry. And I'll simply go ahead and apply that. So now we've got a preserve, and you see it's a little tough to see. It's kind of pale, but there's a green boundary shown around that object now. And it's just letting us know, identifying that that's a preserved region. I'll go ahead and do the same for some of the other mounting holes. Notice they're different size. Some of these are different sizes that we've previously seen already. So I'm going to go ahead and select a new location. A little bit laggy today on the computer. So there's the diameter. Again, that's a smaller hole, so we'll use a 0.2 for the bearing surface at the head of that, and apply that. So I'm just going to be walking around doing this a few more times in some of the areas that are important. The system will catch up with me. A little bit slow here. Not slow, actually. So a few more fasteners here that we're going to fix in place. So, and again, another diametral region being assigned there, and the diameter, or the radius, I should say, that will be, that's a small one, so we'll go with a 0.2 on that one. Hopefully you're not seeing the line by hand. We'll apply that. We'll do the same here. With a 0.2. Risk of looking repetitive and redundant here. And then I'll do the same on this little bit larger one that's down here in the pan. It's not there. It is. We've got another one that's going to be a 0.3. So I'm really just going through the process of preserving what's important about this design. Do the same, just a couple more here. Normally I'm much faster with this. The computer's being a little slow for me today for some reason. So this also is a 0.2. Like that. And I'll just okay that. That's the final one of the fasteners that we were trying to preserve. So if you take a look from the front, a little more clear. We've got some preserved regions, and these are all bolt holes currently. One of the things that, in addition to those keep out areas, we've got interlocking tabs that are going to help us tie or interlock with the adjacent panel on this particular design. This is a bit of a strange shape, but we need to preserve those tabs so that the interlocking nature of them are kept and it works. So what I'm going to do here is, first step is make things a little bit easier for me to select. I'm going to go ahead and rotate. Use the standard Inventor commands for rotation, and our old friend function F4. And I'm just going to rotate that around a little bit so that I'm not so quite askew with the features that are on that face that angle. And then that's going to help me, because when I get ready to preserve additional regions, I'll be able to window select that a little bit easier. So in this case, rather than picking a circular edge like I did with the holes previously, I'm going to go ahead and just pick a point. And because a point's a bit ambiguous, you could end up with either a cylindrical object, likely not, but possibly. You'll notice here that this region has automatically chosen the box. Now I've got multiple arrowheads here that allow me, these manipulators that allow me to make a change. So we could manually make an adjustment here, picking a cylinder if it was something that just mistakenly chose and gave me the wrong different default. But in this case, the box is what we're looking for. So we're going to go ahead and go with that. And then I'll just drag out, again, these manipulators. I want to make sure that I'm creating a bounding area that encompasses all of the important features to be essentially ignored during this process. You could always put in very deliberate values. You see, again, as I'm doing the dragging process here, where those updates in the fields in the dialog box that are updating to help us with that representation. So now I've kind of included, trying to encompass here, a little bit different area for our purposes. So the key here is to preserve what you need preserved in the existing design. I'll go ahead and choose OK. And then that will apply those preserves. Again, as we go through here, you'll see in the browser that we're fairly accustomed to as Inventor users. We've got all of these preserved regions that are being identified, and I could delete them, I could add new ones, I could change their diameter and location and distance and size and those types of things. So we end up with a pretty good control over those options as well if we need to come back and make adjustments for any reason. All right, so if I can get my Inventor coming back to life here. All right, so there's my front view. We've got our loads, our forces. At this point, we might want to add into the notion of symmetry to this design. Now, this is not a symmetrical part in any real way. And so I'm just going to be showing you a little bit about the symmetry and what is possible in symmetry. You'll notice that we can define the symmetry based upon the center of mass or a bounding box or a custom localized UCS that we might use. The planes can be used, so existing planes can be used for the purpose of identifying symmetry in your design. Know that you've got that capability. It's not required here. In fact, our part's not symmetrical, so we won't be applying symmetry. However, you can apply symmetry, it's a great idea because it essentially cuts the calculation time in half, just basically, and your development time. So if this part was symmetrical, I could have probably just picked a couple of those holes and assigned symmetry, which means I wouldn't have to define all the holes. So it just cuts down my workload and also the processing workload that your hardware might find. Speaking of which, these calculations that we're going to be doing using generative design are done locally. They're not cloud-based. I'll also point out the fact that if you feel like this is a good workflow for you and find this interesting, there are limitations with some of the capabilities on the Inventor-based generative design. The Fusion 360 generative design tools have a much greater capability as well as different solution types, etc. What you've seen here, loads and forces, are more mature. I don't know if you want to call it that or not. But this allows us to get our feet wet, get an idea of whether the technology we're using this technology might be useful for us. So now that I've developed or gotten preserved, shown symmetry, what we're going to do now is go into the settings with the shape generator. Again, just moving left to right across the ribbon. We'll see that this is the information about what we want to accomplish. So this is almost like the goals that we're looking to set. So there's this information about the existing mass. And I could reduce that. I could say, look, I would like this component to be reduced by 20% of its original mass. I can also do something like add a target mask, and that's what we're going to do. We know we want this to be a certain weight. We're just not sure how to get there, where to remove the material from without compromising the integrity of the design. So in this case, we want it to be half a pound of mass. We also have controls here with mesh settings. When it comes to refining and meshing, we want to make sure that we're not going overboard here. I could set this mesh setting to be very fine if I was near the end of my design process, or if I'm in the beginning stages of my design process. I might want to make this a coarse, because the calculation will be much quicker if we do that. So I'm going to set that to a fairly coarse value for the mesh. So that's what the generator is going to go to work on using the settings that we just provided. We can transition over to the mesh view, get a little bit closer look at that mesh to see how we've done it, how, based upon the sizes of the features, you might want to refine the mesh if you've got a lot of small features, etc. But with our first run on something sort of planar in this case, we'll take a look at this mesh, and it looks pretty good. You can see the faceting here. Some of the areas where we probably could refine the mesh or use a smaller mesh would be in the tighter areas around the corners and where the hole penetrations are, etc. So that's the creation of the mesh, the review of the mesh, and then we simply going to generate the shape. We're going to let the software go to work on it. And this is going to take a couple minutes. I actually was hoping to just preview one that I already pre-baked. But for some reason, it didn't show up in our interface today. So I'm going to go ahead and run the simulation. Now notice that there's a dialog box that comes up. It'll actually check your work. If there's any deficiencies in the setup that you've done, You don't have a load where you should have a load, and load's completely missing, or if there's issues with the mesh size that was generated that we chose manually, it's within the boundaries or outside the boundaries of what is allowable. For example, you set a mesh size that's so large that it doesn't even, it wouldn't be effective. There's nothing for it to calculate against. That would be certainly something. Missing supports, missing loads, and those types of things are typically what it would find. So in finding those, you'd get the feedback in the lower portion of this dialog box, kind of giving you some guidance as to what was wrong and a suggestion on how to improve it. Again, this is we're calculating these results live on what appears to be a fairly sluggish computer today, so apologize for the delay here, but when we're talking about the amount of work that it's doing in the background, it's not a significant delay, and what a great opportunity to go freshen your coffee or take that much needed bathroom break. So we'll give this a couple minutes to let it finish its work. I guess the benefit here is that it's not a canned routine. So that's live calculation time based upon a reasonably, mediocre mesh setting, etc. Interesting what we get here. It has gone in and calculated where material can be removed from. It did that around or avoiding all of the areas that we set as our preserved geometry. So we see opportunity here for material removal, significant material removal, and it's not anything like the triangular shapes that are the previous effort made, and it's also more significant. If we wanted to take a quick look, it might be a little small to see on the screen, but you'll notice up here that it is also feeding back to us the results of its efforts here. So there's the original mass, and it also is providing us with the new mass, which is 0.5, which was our setting, our boundary. And it also throws in the percentage because we wanted a total mass. It tells us what the percentage is of reduction, and that's a 56% mass reduction. So we've done pretty well so far, getting some results out of this calculation and effectively staying clear of the important geometric areas that shouldn't be modified. The next task at hand is for us to use this shape against the 3D model in the background that is just the sheet metal environment of the model that we're working against right now. So nothing's happened other than the fact that we've gotten an outcome of this calculation. We've given it criteria and we said, go do the work, show us what's possible. What do you think? What are your foresights using AI, essentially? Where can we remove material safely and still distribute load effectively and evenly, consistently across this model, this design? So that's what we'll do next. We're actually going to promote the shape. So the mesh that gets created that we're seeing here has that strange organic shape to it, will be promoted into a physical object. So one of the things that we could do is we could choose where we want that mesh to exist, to reside. If we were doing additive manufacturing, 3D printing type of stuff, maybe an STL file is exactly what we want. We could print this part out with this mesh being part of that printing process. In our case, we're just going to use it as a reference. We're going to use these boundaries that have been created for us as a simple reference, which means we want to propose it. We're going to promote it into a part file, into the existing part model. So when I select OK with that option set, it will give me information about it being added. So it's actually taken the mesh and added it in as a piece of geometry in our browser. I'll go ahead and select OK here and then show you where that ended up. So here's our model and the mesh feature that was added to it as an object. And that's helpful because I can do things like, well, let me just give it a look at it from the front here. And then I'll go ahead and just toggle off visibility on this mesh. So right now, we're going to want it on. But in some cases, you might want to do some comparisons. You could have multiple studies, and you can toggle back and forth between the different meshes that have resulted based upon maybe some criteria that you have changed. So it's nice to be able to remove that from view so that it's not causing too much confusion or complication. In our case, we want the visibility on because we will be using it as a reference as we start to walk around and create physical boundaries, cut away the material on the model sitting behind this mesh. And that's exactly our next step. So what I'm going to do here is go ahead and start the process of defining those boundaries. Well, how do we cut material away from an existing model in Inventor? We create a sketch and we extrude. That's exactly what we're going to do here. So all the things that we're familiar with and comfortable with are part of this process. So I'll create a new sketch. Again, I've got a model that's sitting here. This is just a mesh that's superimposed on the face. So I'm creating a new sketch on that model face. And I'll use that sketch to walk my way around the geometry. So one of the things that we can do is we can conform as much as we want to with regards to this. This is a suggestion. This is the superimposition of the calculated offering, and we can make deviation if needed. In my case, I'm going to go ahead and just use a spline object because of the nature of the geometry. I'll go ahead and just pick a point here and then start making subsequent point selections. And I can zoom up and I can get very close and hold very tightly and make very small distance movements between the points if I wanted to in making the selections, just conforming around the boundary that's being presented here. And I'm not going to do this around all three of the openings, just simply because it's an exercise in tracing, essentially. And we can make adjustments to this after the fact if we wanted to, as you know. So there's the closed boundary that we're going to go ahead and do. I'll leave the others out for now, just in the interest of time. So there's the closed boundary. I'll go ahead and finish the 2D sketch. And then I'll start the extrude command, which of course Inventor sees as a closed boundary. And if I wanted to go ahead and do a little isometric here to make it make sense. And it looks like it's cutting maybe the wrong direction. I'll go ahead and make this a cut operation, which then will remove the material. So all I've done is use that mesh as a reference, as a guidance, as kind of an assisting tool. And it came up with geometry that I probably wouldn't have intellectually come up with on my own. You know, the effort that I would make looked a lot like the triangular cutouts in the model we started with, essentially. This can essentially, I consider it to be being inspired by what the software can help supplement my gray matter. In this case, maybe it makes sense now for me to go ahead and just hide the visibility. And so there's that mesh feature. I'll just turn visibility off. And now we're really just looking at our model. All right, so the work's been done. We've modified this model based upon the inspiration from the calculated geometry that we were provided. Again, there's a couple other pockets that I could and should do something with here. The reality is that shape generator shape has done a pretty good job of giving us guidance. Now, if we were to call that good and go to production with what I've just done here, we would be reticent. We really need to complete the process by actually running a simulation against this, a static analysis on the resulting geometry. And so that's part of this workflow. And that's exactly what I'm going to do next. So again, we've got a shape here, and it's a 3D model that I could manufacture to. We could make G code for, or do laser cut or water jet or mill, whatever you wanted to do with it. One of the things that we're going to do now, though, is we're going to analyze this to make sure it's correct, that it's current and works. So what I'm going to do is I'll go back into the shape generator environment here. Don't forget, we left shape generator and went into modeling. So there's that generated shape generator study. If I were to take this and do a right click on it and copy this study, it would give me another generator study, in this case, the generic number 2. So I've got the source generator study that was done, that resulted in the geometry. Now I've got another design that's essentially identical to it. However, if I were to right-click on this study and edit the study properties, I could come in and I could say, let's do a static analysis. And this is a great way for me to adopt all of the loads, forces, and constraints and the work that's already been done on this model. So that's exactly what we're going to do, is we're going to develop a static stress analysis based upon the same criteria that we just ran that resulted in the shape generator design. And it's very easy. Simply select OK and simulate. Again, the dialog box comes up telling me that the study is ready to run. I don't have any deficiencies. I would have been very surprised if I did, because we're using the same boundaries and conditions from the initial development. So now our static stress analysis is being generated based upon the inspiration and changes we made from the previous shape generator study. Again, real time, no smoke and mirrors. The mesh and the amount of CPU and available resources on your computer. Again, this is all being solved locally, so there's no concerns. I will mention again that the nature of Fusion 360 is that it's a cloud-based tool, which means some of you might have limitations in its use because of restrictive requirements. But also, we've got a situation where we can also bring to bear almost unlimited computational power. The idea here is that we can then go ahead and make a report, which makes all of the conditions and results real. So I can make a report. I can change the format here to an HTML, a single file. And you'll see this report just being automated. So there's a stress analysis report. And because it was inclusive and I said to do all, I'm getting the stress analysis report, its results, and all of its operating conditions, et cetera. And I'm also, as an output of this, we see the shape generator results. So all the information in the environment that this design was subjected to and the results are there, mapped out for us, so that we can review them later or pass them along for review by others. So that is the basics of shape generation and why you might use it, how you might use it, and there are a vast number of differences and different applications, et cetera. This is just a simple design that I chose to kind of communicate the methodology. And that's really the whole idea here, is to see this in its context. It's not a design tool. It's not an analysis tool. It's a tool that serves kind of a bridge. It'll bridge the gap and help you help give you some ideas that might make your designs better and more sustainable in the future. Thank you so much for attending today, and the patience that you endure during those live solves wasn't too bad, but certainly when you're watching something work, it always goes in your brain much slower than it's really going. Thanks so much for your attendance and your attention.